Hi everyone, and welcome back to Chem Story. In today's lesson, we're diving into two important elimination mechanisms, E1 and E1cB. Now, unlike E2, which happens in one concerted step, E1 and E1cB go through a stepwise process. That means they form distinct intermediates before giving the final product. We're going to take a look at how each mechanism works, what kind of intermediates are involved, and what conditions tend to favor each one. By the end of this lesson, you won't just recognize E1 and E1cB on paper, you'll be able to spot them in real reaction scenarios too. All right, let's get started. Let's start with the E1 reaction. E1 stands for elimination unimolecular, which tells us that the rate-determining step only involves the substrate. The mechanism happens in two steps. First, the leaving group leaves and a carbocation forms. Then, a base removes a beta hydrogen and a double bond forms in its place. Since the first step is slow and only involves the substrate, E1 follows first-order kinetics. So the rate law looks like this. Rate equals K times the concentration of the substrate. Here's why that matters. E1 often competes with SN1. That's because both go through carbocation intermediates, and they happen under similar conditions. And that also means E1 reactions usually have low selectivity. You might get a mixture of products, especially if rearrangements occur. Oh, and one more thing. E1 reactions typically require heat. That's because you're breaking a strong sigma bond, like CH or CX, and forming a weaker pi bond between two carbon atoms. So overall, the reaction absorbs energy. It's endothermic, and that's why heat is often needed to push the reaction forward. Let's walk through a typical E1 mechanism using an example. Say we have a tertiary alkyl bromide. First, the bromide leaves, and that forms a tertiary carbocation. This step is slow, and it's the rate-limiting step. Next, a base removes a beta hydrogen, and the electrons from that bond move in to form a pi bond. That gives us an alkene as the product. And here's something to keep in mind. E1 doesn't require any specific geometry, like anti-periplanar alignment, so you often end up with a mixture of stereoisomers. And since you're dealing with carbocations, rearrangements can happen, like hydride shifts or methyl shifts, which can totally change the product you expected. Let's take a look at the E1 energy diagram so we can really visualize what's going on. The reaction starts with a stable substrate and a weak base. As we move toward the first transition state, the energy goes up. This is where the carbocation forms, and it's the most energy-demanding part of the process. Then we hit the carbocation intermediate, which sits in a little dip on the energy curve. After that, the energy rises again, but not as much as we approach the second transition state, where the proton is removed. Finally, the energy drops as the alkene forms. As you can see, EA1 is greater than EA2, meaning the energy barrier for forming the carbocation is higher. That's why it's the rate-determining step. Now let's talk about the role of the base in E1 reactions. Unlike E2, E1 doesn't need a strong base to proceed. In fact, using a strong base often pushes the reaction toward the E2 pathway instead. So in E1, weaker bases are actually preferred. And often, it's the solvent itself that acts as the base, especially in solvolysis reactions. For example, water or alcohol can step in and donate a lone pair to remove a proton during the second step of the mechanism. Next, let's consider the structure of the substrate. Since the E1 mechanism goes through a carbocation intermediate, the stability of that carbocation really matters. The more stable the carbocation, the more likely the reaction is to happen. Tertiary substrates are ideal for E1 reactions. Secondary ones can still work, but primary substrates? They're just too unstable. E1 barely happens with them. So if you're trying to predict whether a reaction will follow the E1 pathway, start by asking, how stable would the carbocation be? Now let's talk about leaving groups. A good leaving group is important in E1 because it helps with the very first step, forming the carbocation. That lowers the activation energy and makes the reaction proceed more easily. But here's something that often causes confusion. Having a good leaving group doesn't mean the carbocation is more stable. It just means the group can break away more easily, which helps kick off the mechanism. Most good leaving groups are weak bases, usually the conjugate bases of strong acids. Some common examples include iodide, bromide, chloride, hydrogen sulfate, tosylate, and water. These species are stable on their own, so once they leave, they don't come back, and that makes elimination more favorable. Let's take a look at the role of the solvent. Polar product solvents are ideal for E1 reactions because they help stabilize both the positively charged carbocation and the negatively charged leaving group. They do this through solvation, using hydrogen bonding or dipole interactions. Solvents like water, methanol, or ethanol work especially well because they support every stage of the E1 mechanism, including the transition states. Now let's visualize how solvation helps stabilize the reaction. In the left diagram, you can see how the solvent molecules help stabilize the carbocation. Lone pairs on the oxygen atoms in water or alcohols interact with the empty p orbital on the carbocation through ion dipole forces or electrostatic attraction. And in the right diagram, the leaving group, now negatively charged, is stabilized through hydrogen bonding with the hydrogen atoms of the solvent. This kind of dual stabilization is what makes polar product solvents so effective. Let's wrap up with regioselectivity and stereochemistry. E1 reactions typically follow Zaitsev's rule, which means they tend to form the more substituted and more stable alkene. Since E1 doesn't require a specific geometric setup, like anti-periplanar alignment, the transition state is a lot more flexible. But that flexibility comes at a cost. E1 is less stereoselective. And don't forget, because carbocations are involved, you can get rearrangements like hydride shifts or methyl shifts, which can give you products that are different from what you'd expect based on the starting material. Now let's move on to the E1cB mechanism. E1cB stands for elimination, unimolecular, conjugate base. And just like E1, it's a stepwise mechanism. But here's the twist. Instead of forming a carbocation, E1cB goes through a carbanion intermediate. So how does it work? It usually happens under basic conditions. First, a strong base removes a beta hydrogen, and that forms a carbanion. If there's a carbonyl group nearby, that carbanion is often stabilized as an enolate. Then, in the second step, the leaving group, which is usually a poor one, like hydroxide, gets kicked out. And here's the key point. In E1cB, it's not the deprotonation that's slow. The rate-determining step is actually the departure of the leaving group. So what needs to be in place for an E1cB reaction to happen smoothly? First, you need an electron withdrawing group near the carbanion site, something like a carbonyl on the beta position. That helps stabilize the negative charge. Second, you need a strong base. The beta hydrogen isn't very acidic, so we need a strong enough base to pull it off. Third, the leaving group needs to be poor. Hydroxide, for example, doesn't leave easily, so we need a mechanism that helps push it out. And that's exactly what E1cB does. And finally, the reaction usually happens in a polar solvent. That helps stabilize the charged intermediates and the transition states along the way. Now let's look at a classic example of E1cB in action, the elimination step after an aldol reaction. We start with a beta-hydroxycarbonyl compound, and under basic conditions, it's converted into an alpha-beta unsaturated carbonyl compound. Here's what happens. The base pulls a proton from the alpha carbon, forming an enolate anion. Then, the electrons from that enolate shift in to form a double bond, and the OH group gets kicked out. This is a textbook example of E1cB elimination, and it's exactly how we make conjugated enones and enols in organic synthesis. So, to wrap it up, both E1 and E1cB are stepwise elimination mechanisms, but they take completely different paths. E1 goes through a carbocation, usually under acidic or neutral conditions, and it's favored with weak bases and good leaving groups. E1cB, in contrast, forms a carbanion. It requires strong bases, poor leaving groups like hydroxide, and usually an electron withdrawing group nearby to stabilize the intermediate. So if you're looking at an aldol product in a basic environment, E1cB is probably what's going on. That's all for today. Next time, we'll dive into substitution versus elimination and how to figure out which one wins based on the reaction conditions. Thanks for watching, and I'll see you next time.